Okay, so you are to design a donation campaign. And let's say this is for a 3-day charity event across the US. And the other important details of the problem description are that you should accept like certain details like the customer name, email address, credit card details. But you can also presume that no payment-specific knowledge is required here. You can presume that you will integrate with a third-party payment provider. So third-party payment provider, such as Stripe or Braintree. Okay, so for this system design problem, right, the first thing you want to do is you want to start by outlining your process to the interviewer. So I recommend that you follow the following structure, right? So right at the beginning of the interview, outline what you're going to be doing. This will not only give structure to your interview, but also like give a hint to the interviewer that you are planning on solving this problem in a more holistic way, that you are planning on covering various details like failure scenarios, and you're going to be talking about scaling. All right, so this is the format that we're going to be following. Understanding the requirements and the goals. Essentially, that would involve understanding what the bounds of the problem are. And the next thing you want to do is you want to figure out what the data model or the APIs are going to look like. Next, we'll move on to designing the component diagrams, which is like the high-level system architecture. The fourth step is to talk about failure scenarios, right? We want to build a system that is going to be robust. So we will cover that explicitly in this section. And finally, we'll talk about scaling. That is, how does our architectures change as we get more users or have to deal with more traffic. Moving on to step number 1, which is understanding the goals and requirements. Cool. So I recommend breaking up your requirements into 2 separate sections, right? So on the one hand, you have the functional requirements, and then on the other hand, you also have some non-functional requirements, which we shall cover after. So the functional requirements are really like the product features. What is it that we're exactly building, right? And some of it is going to come from the problem description. So for example, we're going to be building a 3-day charity event. But here the problem is still like super vague, right? What does it mean when we say like it's going to be a 3-day charity event across the US, right? What is the charity for? So these are the kind of questions you can ask in this step. So for example, for this problem, let's say some of the questions we've asked are like, hey, are the users going to be logged in, right? And let's say, yeah, the user will be logged in. And let's say they're going to be logged in and using an app. Cool. Then what is the user experience if the payment fails or succeeds, right? This is another thing you can clarify with the interviewer. Let's say for this problem, you're required to like send an email on payment fail or success, similar to how like Amazon checkout does it. And then another question you can ask is like, hey, what about like a donation that has been made? Is there like a way for the user to check all the past donations that have been made, along with the status perhaps from within the app? So for the purpose of this problem, you can say, yeah, let's say that past donations are visible. But we won't really spend like too much time discussing this read path, but let's say that it is something that we should keep in mind when we're like talking about the system design. So these are some of the functional requirements of the problem. Let's move on to like the non-functional requirements. So this is quite important because this will actually give a very good indicator to your interviewer around your capabilities of thinking around like concepts like availability and consistency and scale. So the first thing I recommend doing is actually coming up with like back of the envelope estimates on what kind of traffic you'll be receiving, right? Which will help you really understand what kind of bounds are you dealing with. Are you dealing with like a problem which is storage bound or memory bound or CPU bound? So here we are dealing with 3 million donations over 3 days, and so basically per day it's basically 1 million donations, and about 6 donations a day. And a day actually has 86,400 seconds, which you can kind of like approximate to 10 to the power 5. So the traffic that we're kind of dealing with per second is approximately 10 RPS, right? So in my Medium article series, I've given you like a list of numbers that you should get familiar with, which will help you do these back of envelope calculations really quickly. So 10 RPS, it's not super high, but it's important to also think about the shape of the traffic, right? 10 RPS is the traffic that we've kind of like averaged across 3 days, but in reality, the traffic is going to be spiky, right? So you can imagine that you're going to get some high volume from densely populated cities during the daytime. Also, like for campaigns like this, often like a celebrity tweet or a celebrity endorsement can really drive up the traffic. So the shape is important here, right? Like we're saying that it's 10 RPS on average, but really, we should build a system that is capable of handling like much more traffic, right? Let's say we're going to be building a system that is capable of handling like 100 RPS, 100 requests per second. So to handle like something that comes to mind is that to handle like ingress traffic, right, we should probably be sharding the traffic across multiple nodes. In reality, 100 RPS is actually not super high. In fact, like a single machine can probably serve this traffic, but for redundancy and for various other reasons, we probably will be sharding this traffic across multiple nodes. Okay, the other consideration should be for the shape of the egress traffic, right? So ingress is traffic that is coming into our system. Egress is traffic that is going out of our system, right? So remember, we are calling like a third party like Stripe or Braintree for our payments, and certain spikes might result in our traffic being rate limited, right? So we should consider using queues or some mechanism to really smooth out the traffic. So egress traffic and ingress. So these are like important concepts to kind of like just keep in mind as we start talking about the RPS and start thinking through the shape of the traffic. Okay, so let's talk about a few key concepts here. The first one is availability. So you want to build a system that is highly available, and the way to do that is via data redundancy. So data redundancy will improve availability, so we want to build for that. Availability can also be improved by moving parts of the system offline, right? So you can make parts of the system asynchronous, so retries can happen. And in order to do that, we will generally incorporate queues. Okay, so the second thing to keep in mind is latency. Okay, when you think about latency, you should immediately think about like caching or serving data out of like memory, right? So for our donation for this charity app, static content such as like the charity image and text can likely be served out of memory or from a cache. You can imagine that we use a CDN to serve this information, which are like these content distribution networks that are generally geolocated much closer to the user who is requesting for this information. To be honest, like latency is probably not a primary concern in this design because we are mostly focused on the write path, and users are a little more tolerant of write time latency than read time latency. But it's just something else to keep in mind and then talk about, so your interviewer knows that you are like thinking about these concepts. Okay, the next thing is throughput. Okay, so we should design a system that can handle 100 RPS. And although a single node can handle this, we should partition the traffic across multiple nodes to increase the throughput and also for redundancy, right? We can also like partition across different data centers. So you can imagine that for this donation app, we have a data center that's closer to the west coast of the US and one that's closer to the east coast. And this will not only allow us to like increase the throughput, but also increase the availability as well as like reduce latency, right? Because you're like going to a data center that's like much closer to you. However, there is a trade-off here, as it shifts the complexity to read time, right? Because you don't really know which data center the write went to, right? Like if you're like in New York and the data center, the East Coast data center is down, right? Your donation was written to a data center that's on the other side of the world. So you might need to like scatter gather across nodes since the writes could happen on either node. Okay, and finally, let's talk about consistency. So, in large-scale distributed systems, eventual consistency is adequate, and it is adequate here as well. So, you'll see as we get into the system design, a large-scale system will have several subsystems which might independently track state. And it's not always possible, for them to be consistent, to be strongly consistent, right? It's adequate to shoot for eventual consistency. The other thing to keep in mind is read after write consistency, which really means that once a user has made a donation and they go to like their history of donations, like their past donations, they should see the donation that they have made. Otherwise, the user is going to get like a little upset that, hey, I just like made a donation, where is it? And there's many ways to like to actually provide read after write consistency, but a common way is to serve the reads from the writer node, right, for some time after a donation is made. Because the reason why you don't see read after write consistency is because suddenly your read path is hitting a node that is not caught up, right? It's reading from a replica that is still lagging behind. So by serving the read from the writer node itself, the leader node, you can basically ensure read after write consistency. All right, so let's now talk about the data modeling and API section. So first and foremost, let's start with like a high level, I guess, observation or comments about the design that we will be building. Okay, so we want to design a reliable system that can handle donations at scale. So I think the interesting thing here is that we do have like a third-party dependency on a payment provider like Stripe or Braintree, right? So imagine that a user of our donation app, tries to make a donation, but the third-party provider is down, right? Maybe they're having some internal issues, or all requests are timing out. So what should we do at that point, right? So you want to like design an architecture that can handle that scenario, right? So in the happy path, when everything's good, your provider is online, a user makes a donation, right? Everything maybe happens synchronously, and the user can receive a confirmation that, hey, things are working well, your money has been accepted, and they will be notified via email or a push notification. But what about the unhappy path when the payment provider maybe is having issues? So I think a good strategy here could be potentially to make an attempt at like a payment attempt for a donation while the user is online. However, if that payment attempt fails for reasons such as the provider being down, we don't just tell the user, hey, come back later. What we would do is we basically tell them, ideally, a good user experience is that, hey, we tell them, your payment is pending, and we'll let you know when the status changes. By the way, that's very similar to what Amazon does. So if you use like a bad payment method on Amazon, you won't necessarily get a decline synchronously when you're like checking out. What will usually happen is that you will get like an email saying that, hey, actually Amazon goes one step further, and they actually tell you that, hey, your order has been placed, things look good. But then you can receive like an asynchronous email a few minutes later saying that, oh, by the way, your payment got declined, so sorry, try again. You can go in and fix it. So generally that's the kind of experience we do want to build for. But coming back to the data model, right? So we let's start by outlining all the entities that are involved in this design. So you have like the user, right? And the user will have like a user ID. Remember in the requirements we mentioned that the user is using an app, so I'm presuming they're like registered, and the user database will have details such as their name, their email address, profile picture, whatever. And so that is definitely like one entity that's going to be a participant here. The other one is going to be so let's say for this example, right, the user actually can save their payment method, right, and they can even like go and like manage the payment method. So they can go and remove it or add it. Sometimes payment methods can expire, so they can go and update it. So there's a second entity that is involved here called the payment method. And the payment method will have a unique payment method ID. Let's say that's going to be the primary key, and of course you have probably like a foreign key, so you can quickly look up like there might be an index on this, so you can like quickly look up all payment methods that belong to a user, and a status. Like a payment method can be expired, or is it active? Is it in a good state? And other information like last four, CVV, other information about the payment method. And in terms of like the relationship between user and a payment method, a user can have many payment methods, but one payment method will only belong to one user. All right, so a donation, let's talk about what a donation really is, right? A donation is an intention to give money, right? So when I'm donating to like a charity, what I'm saying is that, hey, I intend to donate like $10 or give away $10 of my money to the charity. So that is kind of in a sense different from a payment attempt, right? So, based on the system that we were describing, that, hey, we want a system that is robust, and if a payment attempt fails, right, we will try that again later. It makes sense to actually separate out these two entities, right? So on the one hand, we have this concept of a donation, right, and then related to this is the concept of a payment attempt, right? So you can imagine that a donation can have multiple payment attempts, right? We may like attempt a payment with one card, but maybe that fails, and in that case we will may attempt a payment with a different card, or we may even attempt the payment with the same card if the provider is down. So one donation can essentially have many payment attempts, and a payment attempt will only belong to a single donation. The donation will have a donation ID, which is the primary key, of course, and it has probably like a bunch of indices or like also foreign keys like the user ID. I guess we also need to track here the amount, currency. I think an important one here is the status, right? So what happens when, like, for example, when the user makes a donation and there is like some kind of like timeout or something from the provider because the provider is down, right? What do you do? What should the status of the donation be, right? So it makes sense to have like a status, which probably, a donation would be created in a pending state, and then If it succeeds, it would be marked as success. If it fails, it would be marked as fail. Of course, we would our system would need to have business logic which decides at what point do we actually mark a donation as being permanently failed, right? Because it can happen that you make a payment attempt, it fails, but you try a few more times and eventually it succeeds. So we need business logic to kind of handle this state. Okay, the payment attempt is also quite interesting. So you have the attempt ID, which is going to be the primary key here. And then you have a donation ID, right? This is going to link a donation, a payment attempt to a donation. And it's probably also important to have the payment method ID here. And this again is going to be the foreign key. And the payment attempt itself actually could have a status too, right? So donation can have multiple payment attempts, right? So how do you know whether the donation is ready to be moved to a successful state, right? And I think you can basically use the status in the payment attempt to figure that out, right? If the status of the payment attempt, of the last payment attempt is failed, it means that, hey, our system can still retry, try more payment attempts. But if the status of the payment attempt is succeeded, it means that the donation was complete. All right. The other thing worth calling out is that the payment attempt is associated with a payment method ID. So in terms of the relationship between the payment attempt and the payment method ID, a single payment method can be associated with many payment attempts. However, one payment attempt actually belongs to exactly one payment method. Okay, now that the data model is pretty much laid out, right? It's the question is what database should we use, right? So Dynamo, for example, can support Dynamo and other NoSQL databases can support high throughput, and then relational databases, like Spanner and basically MySQL, they have different features. For example, they might have better support for transactionality, and there are certain database guarantees. So to answer this question, it's important to look at our query patterns, right? So that's how you decide what should the underlying database be, right? So here for the system that we're trying to design, right? If you look at the query patterns and what our requirements are, so first of all, we want to mutate state of the donation table as well as payment attempts and keep those two states actually consistent, right? So having atomicity would be pretty beneficial, right? So NoSQL or Aurora, which is AWS's relational database, systems like that could be beneficial here. It kind of boils down to how we are going to architect the system. So for example, if the payment method if the donation table and the payment attempt table was a part of the same service, then we could definitely benefit from transactionality, right? We could mutate the state of the donation as well as the state of the payment attempt together. However, in microservices architecture, right, it's a common practice to actually have a single responsibility for each microservice. So you can imagine you have a donation service that may interact, that'll call the payment attempt service anytime it needs to make a payment. And if we actually go with that model, which is actually the architecture I'm gonna recommend in this interview, right? If you go with that model, the query patterns become very simple, right? So you basically are doing puts and you're doing gets. A put is basically creation of an entry, right? So when a request comes in for a donation, you will actually create a donation entry, and then you'll call the payment attempt service. And therefore, a NoSQL database like Dynamo or even MongoDB is a pretty good choice here. I will spend just a few seconds just talking about the APIs. And honestly, in a lot of these systems, in these system design interviews, once you've already covered the data model in great detail, you might gloss over or go over the API section really quick because the APIs tend to there tends to be a lot of overlap between your APIs and the data model. But let's say for this system design we are using protobuf and gRPC over HTTP. So your request would look something like this. I'm just going to write it in like protobuf format. So you have create donation request. And you can imagine that it has fields such as user ID, and then payment method ID to identify the payment method you'll be using, then the amount, the currency, etc. Right. And the response is going to be similar. You have the create donation response. And it will return the status. So for example, if the synchronous payment attempt failed, you would return like the status of the donation, which would be like pending, and maybe something else like a donation ID. Right, and the final thing to keep in mind is that this I just like wrote out the request and response protos for the client to server interaction. So these are like our front end server APIs. Internally, as we think more about like the micro architecture design, donation is probably going to be its own service. Payment method, it's going to be its own service, right? So we haven't really talked about the APIs at that service layer, right? So for example, for the payment attempt service, right, we would need to create like a request APIs, an API that would allow you to like create a payment attempt, right? So we'll look at that in the next section. All right, so let's move on to the third part of the interview, which is the system design. And here we're going to draw like the high-level system architecture. We're going to draw out like boxes representing the different services, and we're going to talk about like how they interact. Now, in these in this system design section, you can draw like a client, and you can draw a box representing like the API gateway or the front-end server, which is responsible for like managing the connection. It might be responsible for authentication or SSL termination. But honestly, the meat of the problem is, and this is probably what the interviewer is looking for. The meat of the problem is like, how does the donation, the payment method service, how do they interact, right? So let's start off by drawing this box representing the donation service, right? And eventually, like the client will call the API gateway, which will call the donation service to make a donation. And the first thing that the donation service needs to do is, because it's remember it's receiving like a payment method ID, it actually needs to look up the payment method, right? So there might be like payment credentials or like details about the payment method, like the last four that are required to be passed to the to Stripe or Braintree. So we will also have like a payment method service. And really, the donation service is going to call this one. Finally, once the payment details are retrieved, the donation service is now going to try and call the let's call it the payment attempt service. Okay, don't forget, right, that we also need to like interface with an external, third party like Stripe or Braintree. So let's like just create this cloud. We're going to call it like a payment gateway. This is the third party payment gateway, right? So when the donation is about to be made, you look up the payment method. In the happy path, you call the payment attempt service, which is going to like try and make a payment attempt. And this payment attempt service will actually call the external third party Stripe or Braintree. And the happy path, everything is good, the payment succeeds. Stripe says okay, you return the response back to the client. Life is good. All right, but what happens in the scenario when there's a failure, right? And specifically if it's a retriable failure. Now if it is like a hard reject from the payment gateway, right? If the payment gateway says, well, these credentials are wrong, etc., right? We would tell the client that you need to use a different payment method or add a new payment method. But for like these transient failures, we need to retry, and we can't like just have the client waiting, while we keep retrying, right? Like users aren't really that patient. It's annoying for them to constantly see a spinner, right, going on for like like a couple of minutes. So What we would do in this state is that, when if there's the transient failure on the payment provider, we would return to the client a pending status of the donation, and at the same time we want to like kind of schedule like a callback, right? We want to schedule something asynchronously so that like retries can happen later. So in order to accomplish this, essentially you're going to be using queues in some capacity, right? So you can use many different solutions for this. For example, like Kafka could be one way to do it, right? So you queue this message into Kafka, and then you'd have to set up like configure consumer groups that kind of read from the queue and process process the message appropriately. Now, a lot of like services, and we have this at like Google and Lyft, and at many companies that I've worked at, you have like services that are like task queues, essentially, right? And these are services that can be used to schedule callbacks. So basically, what you do is you call the service and you say, hey, listen, I need you to call back, at this destination at some point in the future, right? So you're essentially scheduling callbacks. So you can imagine that if in case of a failure, right, the donation service marks the donation as pending, and what it does is it basically enqueues something into this task queue. Now imagine that this is a service that at some point will wake up and it's going to have like internal workers. I'm not going to focus on it. I think it would make the design just more complex. But the assumption here is that there are these workers that will like look at like the messages in the queue, and the consumers will actually schedule a callback. So we will schedule like a callback back to the payment attempt service to make another payment attempt, right, at some point in the future. And that is how the scheduling will end, right? So imagine that in the future, you schedule a payment like 3 hours from the first failure, and then 3 hours later, task queue calls back the payment attempt service. The payment attempt service basically looks up details. Like it may need to call the payment method service to get like payment credentials or payment details, and then it will attempt another payment. It'll call the third party again, and if it succeeds this time, it will update the status of the payment attempt. And once the status is updated, it needs to actually also go and do a couple of things, right? So remember that our donation service has a status, right? And the initial status of the donation service is going to be pending, right? If a failure happens. So once these callbacks actually succeed, right, the payment attempt actually does this processing offline and actually succeeds. We need to like ensure that the donation is the status of the donation is consistent with the status of the payment attempt, right? And this is what is known as like basically eventual consistency, right? Eventually, the donation which has a payment attempt that succeeded must move to the status like a succeeded status. And in order to do that, right, once this payment attempt succeeds, we again need to like somehow notify the donation service. And we need to not just notify the donation service, we probably also need to notify a notification service, right? The notification service is going to go and actually send the email to the user and say, hey, listen, things are good, the payment succeeded. So this can be done in many ways, right? The payment attempt service could directly call like the donation service, and it could like also make a post request to like a notification service, right? We actually need like a notification service here. We haven't actually talked about like the state, etc., and that is a whole story in itself. But basically, the payment attempt service needs to call the donation service, needs to call the notification service, so that they can like update their state appropriately. And honestly, you're probably also going to not do this, synchronously, because calling, the donation service will essentially creates like a hard dependency, right? On it tightly couples the payment attempt service with the donation service. So what you really want to do is you want to actually use like some kind of a queue. So you can imagine that there's again, we schedule something into task queue, and this queue will basically call the donation service to update the state, and it will also call the notification service, which will be responsible for actually sending, the success notification back to the client. So this is essentially how like the system would be designed. Now you can even take this like one step further, right? what if instead of like actually making any payment attempt synchronously, right? What if like everything is done async? So for example, imagine that a request comes in to make a donation. We write to our database, we create a donation in pending state, and then we basically just schedule something, like we schedule a payment attempt in the future, right? And we just return a response to the user saying, hey, listen, this will be executed pretty soon, but right now your donation is in a pending state. You'll get an email notification once the payment succeeds. And everything happens asynchronously. So the payment attempt happens asynchronously, the notification happens asynchronously. And now why would we do that, right? I think the main advantage is that your donation itself becomes really quick, right? Your latency is going to be really low because all you're doing is like writing something to your database and queuing something up. You're not like waiting for your third party to give you a response. It can also like help you really smooth out the traffic to the third party, because keep in mind, right now in the initial design that we architected in the happy path, you are making like a synchronous call, right? The user is in session, the user is online, you're making a call to a third party, and you're waiting for them to respond to you. You're waiting for them to tell you, hey, did it succeed or did it fail, right? So what can happen is that if your traffic is very spiky, imagine that a celebrity endorses a charity and suddenly you're like hitting hundreds of QPS. The third party might not be provisioned with that kind of to handle that kind of throughput, right? And that is another advantage of using queues. Queues can actually basically help smooth out traffic, right? Because what you can do is like you can basically start queuing all these requests offline, and slowly you can set like a rate limit or something on the outbound rate, right? So the egress traffic can be controlled, right? We talked about this earlier on in the previous section, but that is another way that you could use this system. Anyway, so I guess another thing worth talking about is that what if like the payment attempt fails like 5 times, right? So how does that happen? So the first time the payment attempt fails, right, we have to make sure that retries happen. Therefore, I think one thing we do need is that the task queue service that we're going to be leveraging on, right, we need to have some notion of like response codes, right? So if the task queue receives a response code that is like, a 500 or some kind of like retrial response code, it should have like business logic to retry at the rate that can be pre-configured. Generally for retries, in large scale systems, we like using the notion of like exponential backoff. And what that means is that you're not like just, your retries are fairly smart. You don't just keep trying once a day. You basically, or like once an hour, you do like an exponential backoff. What that means is that the first few times, you may attempt, you may make payment attempts very like frequently, like maybe like, once every minute, and then you like exponentially back off. So the next attempt is like 5 minutes later, and then like 20 minutes later, then 2 hours later, and then 8 hours later, etc., so on and so forth. Okay, cool. So hopefully that gives you like a pretty good high level view of like how this system could be designed. I think there are like it's worth like kind of like digging into a couple of things. So the first thing to think about is that what happens if the client like starts like makes like duplicate requests to make donations, or for that matter, the donation service could call like the payment attempt service like twice, right? So I think we basically definitely need like this notion of like what is known as idempotency, right? So these services actually need to be idempotent, and what that means is that idempotency essentially means that if you as long as you have two requests with the same idempotency ID or the same idempotency key, these requests should not be treated as two different requests. So both these requests should not be mutating state, right? So typically you basically save like an idempotency key. So for example, you can imagine that the donation service has like this idempotency key field, which could be generated on the client. It could be kind of like handled by the server. So if it's generated on the client, what we're saying is that as long as the client is generating like a new idempotency key, which could be UUID, right, generated by the client, we will treat these as two separate donations. However, if the client uses the same idempotency key, for example, there's a bug that the user clicks twice, but two separate like RPCs or requests are firing in the in the background, we want to make sure that we dedupe this, right? So you can have a field called idempotency key on the donations table. You can have an index on it. So whenever the request comes in, the first thing you do is you actually look up the donation and see if there's like a donation with the idempotency key. If there is, there's nothing to do. You just like return 200. You say, hey, or you just return whatever was the status that was originally returned. And if not, you basically create like a new donation. You could also get like tricky with the fields, right? Like so you can imagine that your idempotency key is derived right from the user. It's derived from the user plus amount plus payment method, right? And here the assumption is that like within like a span of 1 minute, the same user won't use the same payment method to make a donation for the same amount, right? So you could have like some logic on the server. Instead of like having the client derive this, we can like just do some deduplication on the server and say that requests with the same amount, same user, same payment method that happen within like 1 minute, a 1 minute window are actually idempotent. You could even go like one step further and like prompt the user and say, hey, if you've already received a donation for this amount with this payment method, less than a minute ago, are you sure you want to like do this again? And this is a way to like prevent duplicate donation attempts. Okay, moving on to the fourth part of the interview, which is basically the failure scenarios. All right, so this is like a section which is like very commonly overlooked when someone is doing the system design interview. But this part is very important because it basically kind of like indicates to the interviewer that you are someone who thinks about edge cases and corner cases, and essentially you will be able to design a system that can handle failures. Now remember, in like modern microservices architecture, right, we don't want to design a system that never fails. Instead, we want to design a system that can fail and it can handle those failures gracefully. The reason for doing that is because if you design a system to not fail, and if a failure does happen, which it inevitably will, the failure can often be catastrophic, right? So you want to design like a system that can actually handle all kinds of failures. Okay, so let's talk about the different kinds of failures that can happen in this particular donation application. So we already talked about like the client sending like duplicate requests, which will be handled via an idempotency key. But even other than that, right, in a distributed system, microservices architecture, you will inevitably have to deal with like problems of eventual consistency. So consistency is another like failure that can happen. So how would that happen, right? So imagine that you're making like some payment attempts offline, right? And the reason for doing this is because the initial payment, when the user was in session, when the user was online, failed, right? So you have like these offline attempts to make payments to like the third party, and imagine that after trying a few times, the payment attempt actually succeeds, right? So you've finally like managed to like take money from the user, and this can happen. This could have happened like on like let's say the fifth or sixth attempt, right? Now remember, like we track like the state of the donation, like the status of the donation separately in the donation service, right? So now we need a way to actually notify the donation service, right, that the donation is no longer pending. The donation is actually, it has moved on to the succeeded state. And this is probably important because remember, like right at the beginning we talked about like the user is using an application, so they might be like looking at all the past donations, right there. So there's a whole read path, right? So they're probably, the read path is probably querying the donation service to get the latest donation status. So if the donation if the call from the payment attempt service to the donation service doesn't succeed, right, the donation is still going to show as a pending donation, right, even though we've already charged the user. So in that sense, the payment attempt would not be consistent with the state of the donation service. And this is like the classic problem of like eventual consistency that a lot of like microservices, a lot of systems in the real world today have to deal with. How do we make sure that the status and the state across services is consistent? Okay, so what is the way to handle this? How do we ensure that this happens? To be honest, like there's no like very straightforward way. I mean, honestly, like there are some solutions out there, like having cross-service distributed transactions, for example, and that would be one way. but those are very expensive and typically not the right solution in modern microservice architecture. So what you would do usually is like you would maybe have some kind of like a healer or like a cron service, right? Which basically is like kind of polling the status of like the payment attempt and the donation service, and it's trying to make sure that the statuses are consistent. And you can like kind of make that healer even more generic to it could just be a system that kind of makes sure that statuses kind of like match, not necessarily if the latest payment attempt is in a failure state, we want to make sure that the donation is not succeeded, right? The opposite problem, potentially you could have some like bug or some kind of data corruption, and suddenly your states kind of go out of sync. So having a healer like a cron job is a common way to do it. There are like other more sophisticated ways to doing it too, right? Like, so you can imagine that you've build like an external system, like some kind of workflow engine that basically receives like status updates or like events essentially from like the donation service or the payment attempt service. And this workflow engine is like kind of like just tracking the states across services and making sure that the states match, right? And if these states are like inconsistent, it would like page the on-call. So which also again is like a kind of a reasonable approach, right? If this is like if consistency is something that we don't expect to fail very often, it might be okay to actually page the on-call if like the cron job actually, that the healing cron job that you've built actually determines that services are out of sync, they're like not consistent. All right, so we talked about consistency, we talked about idempotency. What else can go wrong? Well, actually a lot can go wrong, right? So imagine that you make a donation. Timeouts can happen always between whenever like inter-service communication is happening. Like the network can have failures, so you imagine that like the donation service is calling the payment attempt service, and then there's just a timeout because of like a glitch in the network, right? So what should happen in that case? So usually, right, in this particular example, you want to make sure that you return some kind of like retriable error to the client, so to the mobile client, if like, for example, the donation service fails, and then the client would simply like retry if it gets like a retriable error. So if like the database is degraded or the donation service has some kind of failures, the client receives a 500, and the client knows that, oh, I should just try again, right? And it can do that in the background as well, right? It doesn't have to necessarily tell the user to retry. What else can happen? Well, imagine that so the various steps we take when a client tries to make a donation for the first time is that we will probably write a pending donation status in the donation database. And then we fetch the payment method details from the payment method service. Then we'll call the payment attempt service. And if everything succeeds, we'll basically write, change the donation status from pending to succeeded. And then we'll return like a 200 OK response to the client, right? But if the database is down, right, we return a 500, so the client retries. Similarly, what happens if we are unable to, call the payment attempt service, right? So if we're unable to call the payment attempt service, maybe the payment attempt service is down. Remember, we will try to like do this offline. So we'll try to like add something, schedule something with the task queue. Now, task queue itself can be down, right? So task queue might return, you're trying to like actually schedule, you're trying to like schedule a callback, but task queue says, well, I'm down, sorry. The task is not in queued, right? So again, in that case, you're going to return like a retriable error to the client, and the client hopefully calls again. Okay, but you can even go one step further, right? So what can happen is that you wrote the donation in the pending state, you call the payment attempt service. The payment attempt service is like, the provider is down. It says, well, the payment attempt failed. So you enqueue something into task queue. Task queue is able to actually enqueue it, right? So it schedules a callback. But a timeout happens before a response can be received by the donation service. So in like in microservices, failures, timeouts can happen at any point, right? So inherently you need to like constantly make sure that your system is able to handle those kind of failures, right? So what would happen in this case, right? Now in this scenario, the task has actually been enqueued, right? Except that the donation service doesn't know that. As far as the donation service is concerned, it basically just gets a response that says, well, I timed out, right? So we need to like build logic, for example, in the donation service itself to to enqueue a task again. And that's why like this notion of idempotency is super important, right? Even when you enqueue the task into task queue, the task queue service should be idempotent, right? It's not like it should basically allow you to enqueue two conflicting tasks, right? So that's one way. However, in most of the cases, actually, these queues will have at least one semantics. What that means is that even if you enqueue the same message twice, or if you enqueue like a message only one time, the task queue can actually call back multiple times. That's true for almost like all queues, by the way. Although like recently Kafka, I was reading that Kafka actually allows you to have exactly one semantics. But the point being that the task queue service may call back the payment attempt service multiple times, right? And what happens if the task queue service calls the payment attempt service multiple times? Do you want to like call Stripe twice? Well, maybe, right? It just depends on the Stripe API. So usually like Stripe APIs and these payment APIs itself will be idempotent. So what that means is that as long as you call Stripe with the same idempotency key, and that key is usually going to be a part of their API, we're fine, right? So as long as these third parties, as long as the gateway service is actually idempotent, the system will actually continue working as intended. All right, so these are actually examples of failure handling at the application level, right? But even beyond the application, right, there could also be all kinds of system failures, right? So for example, you have these nodes and you have databases, and it's possible that your database goes down, or like the service that's your EC2 instance, or however you're hosting a service, it's possible that the node itself it goes down. So we need to have we need to have like replicas for redundancy, and generally you'd have a leader with many reader replicas, and if the leader goes down, the replicas need to be upgraded to basically become the leaders. And there are like nuances and complexities there as well. So for example, you want to make sure that whoever is being promoted to become the leader, right, that replica is caught up, right? Otherwise, you're going to have like data loss. Then there's other questions around like how does the leader election happen in the first place, right? So generally, like you have services like Zookeeper that can help with leader election, and for example, you can imagine that if there's like 5 different follower nodes, like 5 different follower replicas, and the leader goes down, then there maybe there's a distributed transaction, and all the replicas basically try to acquire the lock, and whoever actually manages to acquire the lock becomes the leader. But there's a whole deal of complexity there. You need all the nodes, all the replicas actually need to agree who the leader is. Otherwise, you can imagine that maybe the leader, you thought that the leader was dead, but the leader kind of like is not actually dead, right? And then suddenly you're dealing with problems like split brain, and there's all kinds of nuances that can happen when you're talking about like these distributed database systems with replication. Okay, what else? We've kind of like talked about like the leader and followers in an active passive mode, right? So you have like a single leader, and the followers are kind of like passively waiting. But you can also have like an active setup. So for example, you can imagine that you have these 2 leaders serving writes out of 2 different data centers, and if one of the data centers goes down, then the traffic just gets routed to the other data center. And the trade-off is that we need replication across data centers, and you want to make sure we're monitoring for replication lag, which is basically like a measure of how far a follower is behind a leader, etc. Okay, if you are using queues, I know we talked about like this abstraction known as a task queue, but imagine that you're using like simple Kafka, right? A broker like Kafka, and then you have like your own set of consumers that are like reading from the queue. So a lot of failures can happen there. What happens if the broker fails? What happens if the consumer, one of Generally, it's not just one consumer. You have like a system of consumers known as like a consumer group. What happens if like one of the consumers in the consumer group fails, right? There needs to be a coordinator that kind of like redistributes the work to like, one consumer is gone, so the work needs to be redistributed to the remaining consumers that are like still alive and healthy. Okay, we covered most of the failure scenarios. We talked about the application level, failure handling. We talked about some system level failure handling. And at this point, I think we can move on to the next and the final part, which is basically scaling. Now, partitioning is basically one of the best ways to increase throughput, right? So instead of like serving all traffic from a single node, you can imagine that you spread the traffic, you shard it basically across multiple nodes. And this will basically allow you to like keep more connections open, serve more traffic. So unfair like skewed partitions can result in hotspots. So for example, like basically it's partitions with disproportionately high load, and you typically have like two partitioning strategies, right? You can partition by key range. So for example, for user IDs, you can imagine that users from user IDs 1 to 1000. Will basically go to one partition, from 1001 to 2000 will go to the second partition, and so on and so forth. Or you can also like basically partition based on hash of the key. So right, like instead of like using the user ID, you basically hash the user ID, and the hash, you hash the string to like, let's say a 32-bit number using like MD5 or some kind of like hashing strategy. And you assign a partition a range of hashes rather than a range of keys. And the partition boundaries can be like evenly spaced or chosen like pseudo-randomly, in which case, by the way, it's called consistent hashing if it's pseudo-random. This might like work out better. It might be better at like not creating hotspots, because imagine that like for a campaign, initially there's like a whole bunch of like users that sign up in partitioning based on like the key range, right? It's gonna like go and constantly hit the same partition. However, if we use hashing, then it's more likely that these users will be like distributed across different regions. All right. So in conclusion, we talked about like the requirements and goals. That's how we started, and then we moved on to like the data modeling and the APIs. In the third part, we covered the component diagrams, which is like the high-level system architecture. In the fourth part, we covered failure scenarios and how you could potentially mitigate them. And finally, we spent like a couple of minutes talking about scaling, right? So, it's a lot to cover. Generally in a 1 hour interview, it's very hard to like really dive into the details of a system like this. Generally, a donation system like this would be built by like many people, over many months. And to like, it's hard to do justice to it in just 1 hour. But I think we covered like a lot of like the high level, the most salient features or the important points of this system design. It's also worth like maybe just talking very briefly about like security. Data. This is like payments data, so any information that we're storing has to be like encrypted at rest and in transit. We also mentioned like an API gateway layer that I actually kind of excluded from a system architecture diagram. But generally, you'd have like an API gateway layer, which would be responsible for like user authentication or like SSL, TLS, security truncation. And finally, when designing like a system like this, you have to also think about like, monitoring and observability, right? Like, how do you know that a system is performing as intended, right? So it's important to like track things like, the latency, the P95, how long does it take for a donation request to complete, and set like the appropriate alarms or like a paged on call if the latency looks weak. We also probably want to track the number of like successful donations, and the number of failed donations, and what is the ratio between them, right? So whenever like there's an escalation or an elevation in the number of failed donations, it should like page the on call to make sure that the issue is like looked at and the problem is diagnosed appropriately.